Et voila, I think this was one of my most favorite proofs here on this channel ever, and I hope you did enjoy what you have seen today. I had so much fun. There was such a cool derivation.
Papa Flammy's Advent Calendar.
Good morning, fellow mathematicians. Welcome back to another episode on Papa Flammy's Advent Calendar. And today's video is gonna be an absolute banger, at least in my book. It's going to deal with one of the most amazing properties of parabolas, which is right in connection with all the other videos we did on parabolas in the last time. I know it's not a boring calculus video, so not like 10th grade calculus. It's going to be very nice, so please watch up until the end. It's extremely satisfying. So, you probably know about Archimedes. Archimedes was a Greek guy, if I remember correctly, and he was using parabolic mirrors to light shit on fire. And with shit, I mean battleships, battleships over on the Grand Sea. Now, parabolic mirrors are pretty cool because we have heard about parabolas that they all have a certain focus somewhere. Meaning if light goes in there, then the rays of light get reflected basically and meet right in the focus. And then you can light stuff on fire using parabolas, for example. Maybe you have seen some demonstration of parabolic mirrors before. And what we want to show today is that every parabola does exactly that. Namely that all of the rays that go into the parabola meet in the focus. This is why it's called a focus. In German, it's called a Brennpunkt because it burns stuff. Brennen is burning, basically. It's a burning point, you could say. And now we are going to dive right in. So at first, a tiny little sketch. And once again, we are just going to deal with parabolas that are centered at the origin, meaning they are of the form f of x equal to ax squared. You can use any parabola that you wish, but other than that, it's just a translation in 2D space in some kind of way. For each and every parabola, we know that the focus lies on the symmetry axis, and if the parabolas are of this form, they are just stretched parent functions, then the focus lies exactly at the point 0 and 1 over 4a. This is what we have found out before. Now, how can you put light into a parabola or parabolic mirror and have it meet exactly at the focus? There's only one thing that you really need to take into consideration. Namely, all the rays of light need to go into the parabolic mirror or the parabola parallel to our y-axis. So light must go in here like this. And once this happens, it meets the parabola at a certain point. This point has an x-coordinate. We are going to call it r. And if we plug r into our parabola, because it's part of the parabola, we are going to get ar squared out for the y-coordinate. And once this condition is met with the ray of light, I'm going to call it number 1, getting into the parabolic mirror or the parabola parallel to the y-axis, all of those rays of light are going to go right through our focus. I'm going to call this line segment 2. This is going to become important later. And now I'm going to expand the sketch a tiny bit. I'm going to put it over here once again for this side. This right here is our parabola. And now we have this ray of light. It goes into here like this. This is number 1 once again. This right here is our focus. This right here is the reflected ray of light. This coordinate is at 0 and 1 over 4a. Sketches are very important for this problem because of the geometric interpretation. And now, as mentioned before, what we want to show is that inside the parabola, stuff gets reflected in such a way that it passes through the focus. You probably heard about the reflection law in physics that states if you have a plane mirror and light comes into here under an angle alpha, then the reflection angle alpha prime is going to be equal. So what we basically need is we need a reflecting surface, which is our parabola, and this reflection law holds for each and every surface that you can think of. But one condition, if the curve is basically not linear, like this plane mirror, what we need is a tangent to this curve. So for our construction, what we also need is the tangent that runs right through the point that we have marked out before. And now what we basically want to show is, and this basically proves the theorem, if our rays of light go exactly like this, parallel to the y-axis and then right through the focus, then our condition for the reflection law is met, namely that alpha, this angle up here, is equal to the reflection angle alpha prime right on the tangent of our parabola. This is what we want to show. This is the point of the video. Namely, we want to show that alpha is equal to alpha prime. Now let's get started. It's going to be extremely satisfying. So at first, this right here is our tangent t. So we have to work a tiny little bit with our tangent t, and we are going to put a few more sketches on here and see if we can find a few nice relations. We are going to find nice relationships. Obviously, it's going to be really satisfying. So the first thing we are going to do is we are going to take a look at the slope of this tangent line right here. Now, since the tangent line is tangent to our function ax squared, it must have, at the point where they both meet, the same slope. Meaning what we are going to do is we are going to find out the slope of our function f at this exact point, and it's going to be the same slope as our tangent. By definition, this is how tangents work. So what is f prime? F prime is the same as 2 times a times x. If we now plug in the coordinate, the x coordinate of our point where the ray of light hits the parabola, we are going to end up with a slope of 2 times a times r. This right here is the slope m of our tangent t. Now, we also know something about tangents that we have discussed in previous videos. This is why I made a lot of videos on those. If we have a linear function, the slope is also defined as the rise over the run, delta y divided by delta x. And if we were to put a slope triangle into here, like this, then delta x is exactly this, and delta y is exactly this, for example. Now, this right here is a right triangle. We projected it like this into here. If we were to get ourselves an angle beta down here, then you can find a certain trigonometric relationship between the slope of a linear function and this angle beta down here. Namely, this angle beta that we have here is connected by the tangent. The tangent of beta is the same as the opposite divided by the adjacent. So this thing right here, 2 times a times r, is actually the same as the tangent of beta. But beta is not of use for us. What we want to find out is the connection between alpha and also alpha prime in some kind of way. So we need to kind of connect our beta to our alpha. And this is where the first sketch really comes in. And for this, I'm just going to expand our sketch a tiny little bit. So what we have here is we have our line, which is parallel to the y-axis. This is number 2. And we also have our tangent, which goes like this. And now it becomes really apparent. This right here is our tangent. So by definition, this right here is the right triangle projection. And this right here is our angle beta. Now, this up here is alpha. If you compare the two sketches, this right here is exactly alpha. So meaning, since on a straight line, this must be 180 degrees. This angle right here is, for example, gamma. So since we have a straight line, once again, this right here must also be alpha. So you probably see the connection here right now. And this is one of the most important things that we later need. Namely, since the interior angles in the right triangle, or just triangles in general, add up to 180 degrees, which is par overall. And we already have par over 2 over here because it's a right triangle. We must have that beta plus alpha must add up to par over 2. Or in other words, if we were to subtract alpha, we are going to get that beta is nothing other than par over 2 minus alpha. So we have for the slope of our tangent, m of t, that the tangent of par over 2 minus alpha is equal to 2 times a times r. And this right here is going to be extremely important. Same with this relationship. Now this right here made use of our first ray of light and also our tangent. So we already have brought a connection to alpha from those two structures. Now it's all about getting an argument for alpha prime. Namely, we want to show that alpha prime is the same as alpha. And that's where it becomes a tad bit more complicated. And for this, I'm going to draw out our ray number 2 as a linear function, as well as our tangent t and this projection, which turns it into a right triangle. So for the ray of light number 2, this right here is going to be an entirely new section. This is going to be the sketch for it. Now, what we have, this right here is the linear function number 2, which symbolizes our second ray of light. This right here is our x-axis. This right here is the extension of our ray of light number 1. This right here is going to be our tangent line t. Now, what we know is that up here in the corner, this right here is alpha prime. We also know that this right here is going to be alpha. That right here is a right angle, and we know that this right here is beta. This is a straight line, 180 degrees, par. Meaning what must this angle be? This angle right here must be par minus beta. And this angle over here is delta. We don't know yet what it is, but number 2 is a linear function. And the linear function, the slope of it, this is the only thing that we are interested in when it comes to the angles. The slope of this function is exactly the tangent of delta. So for number 2, we have that the slope is the tangent of delta. But it's also the rise over the run. Now, what is the rise over the run here? We can just take 2 points on our linear function, because if you connect 2 points, you uniquely determine a linear function. And delta y and delta x, well, they are just the differences in y coordinates and x coordinates. Now, what is the difference in our y coordinates? The difference in y coordinates is 1 over 4a minus a times r squared, or the other way around. So delta y is the same as a r squared minus 1 over 4a. And all of this divided by the difference in x values, and the difference in x values is r minus 0, which is r. And now what we can do is we can just drag out the fraction a tiny bit. So this right here is the same as a times r minus 1 over 4ar. And this might not seem very spectacular, but here is where something really cool comes in. Take a look at what I have marked here. 2 times a times r is the same as the tangent of par over 2 minus alpha. Okay. Now, there is a 2 times ar in here, twice actually. So we have 2 times ar divided by 2 over here. Also, we have 1 over 2 times 2ar, because 4 is 2 times 2, obviously. So we can actually rewrite the tangent of delta as the following. The tangent of delta is the same as 1/2 times the tangent of par over 2 minus alpha minus 1/2 times, and 1 over the tangent is the cotangent. So this right here is the cotangent of par over 2 minus alpha. And we can factor out the 1/2 on both terms, giving us 1/2 times the tangent minus the cotangent of the same argument. And this is where the really satisfying part begins, because this right here actually leads to an addition theorem that I have not known of before. It's satisfaction pure. It's just simply amazing. So please keep watching for the watch time. I need the engagement. Okay, but no, on a serious note though, this is gonna be amazing. So at first we are gonna do some black magic fuckery with our trig functions. So both tangent and cotangent are odd functions, meaning what we can do is we can drag a negative sign to the outside, turning the sign inside around. So what we are gonna end up with is that the tangent of delta is equal to 1/2 times negative the tangent of alpha minus par over 2 plus the cotangent of alpha minus par over 2. How is this useful? Well, now it just makes it a little bit easier to see the shift in the functions. What we are just going to do is we are going to shift the tangent and also the cotangent pi over 2, so 90 degrees to the right-hand side. I had to think which direction to point because of the inverse with the camera, you know. So to the right. Okay, so if we shift it to the right, tangent is the sine over the cosine. So if we shift the sine to the right, the sine turns into the negative cosine and the cosine turns into the sine. Meaning the tangent is going to turn the hence into the cosine over the sine, but with a negative sign in front. Cosine over sine is just cotangent. Negative and negative becomes positive. So overall this turns into 1/2 times the cotangent of, and the pi over 2 disappears. This is just alpha. Now the cotangent by the same argument is cosine over sine, but if we were to shift it pi over 2 units to the right, we are going to end up with a negative sign in front, and the cosine turns into the sine and the sine into cosine. So this is just the tangent of alpha. Okay, very cool. We already came pretty far. And now we are just going to make use of the simple definitions of the cotangent and the tangent and play around with the fractions a tiny little bit. So we are going to rewrite it into its representative forms of, so the tangent of delta is hence equal to 1/2 times. And here we are going to get for the cotangent of alpha, this is the same as the cosine of alpha over sine of alpha. And then minus the sine of alpha divided by the cosine of alpha. Now, just expanding both fractions by cosine over cosine and sine over sine, what we're going to end up with is 1/2 times, this is the cosine squared of alpha, I'm going to leave the alpha out for a second, minus the sine squared divided by the sine times the cosine. And now you should scream at your screen right now, because this is just absolutely fabulous. Are you noticing something? I'm going to track the number 2 down here. Cosine squared minus the sine squared is exactly the double angle formula for the cosine. So if we have the cosine squared of alpha minus the sine squared of alpha, this is the same as the cosine of 2 times alpha. Vice versa, 2 times the sine times the cosine is the double angle formula for the sine, and this is just simply amazing. This right here is the sine of 2 times alpha, meaning this addition formula for now, so 1/2 times the cotangent of alpha minus the tangent of alpha, actually turns into the cotangent of 2 times alpha. It's kind of a double angle formula for the cotangent, which is really amazing. I didn't know about this before, but it gets even better with a bit more trick fuckery. Now, what we are going to do is we want to turn this expression with the cotangent into a tangent. Reason being that we can then use the inverse tangent on both sides, giving us overall just the arguments. We need to be a bit careful here when we do this, just because of the domain of the tangent and the invertibility. But for now, how can we turn the cotangent into the tangent? Well, by shifting it by pi over 2 in either direction. This is where we need to be careful. So what we are going to do at first is we simply going to add plus pi over 2 minus pi over 2. We don't change the argument in here inside of the cosine or the sine, but it's gonna turn the thing around once we shift it. So meaning, what we are going to do inside the arguments, we are going to add pi over 2 over here, and we are going to subtract it once again. Same down here, divided by the sine of 2 times alpha minus pi over 2 plus pi over 2. Now, here is where it becomes really important. If we want to invert the tangent later, meaning we want to use the arctangent on both sides, the inverse functions. The inverse function is only defined if the argument is bounded between a negative pi over 2 and pi over 2 inside the argument of the tangent. Now what were to happen if we were to shift our function, so use negative pi over 2 to the right? Well, then we would have a problem, because then we would have a tangent argument of 2 times alpha plus pi over 2. This is gonna overtake our maximum argument, obviously, because alpha is non-zero in our case. At least this is what we are gonna deal with. And this sucks, because then our tangent isn't invertible. So we need to move it into the right direction and the pi over 2 to the left-hand side, giving us overall the cosine of, no, not the cosine, I'm terribly sorry. Cosine turns into sine, and if we were to shift the cosine to the left-hand side, we are going to end up with the negative sine. Now, so wird es Schuh draus, this is how you get a shoe. That's just a German saying, is absolute dog shit. 2 times alpha minus pi over 2 divided by, and the sine, if we shift it to the left-hand side, the sine is going to turn into the regular cosine. 2 times alpha minus pi over 2. Okay, very nice. So this right here is now the negative tangent of 2 times alpha minus pi over 2. Now the only thing that we really need to do now is we need to turn both expressions into just tangent being equal to tangent, but since the tangent is an odd function, we can track the negative sign into here, leaving us overall with the tangent of delta being the same as the tangent of pi over 2 minus 2 alpha. And now we can use the inverse function on both sides, giving us, by comparing the arguments, that delta is the same as par over 2 minus 2 times alpha. And this is where the grande finale starts, because we have a triangle in here, and all the interior angles of a triangle end up to par. Now this triangle has certain angles, namely delta. We also have alpha prime, and we have par minus beta. So plus par minus beta plus alpha prime. But we know what delta is. This is exactly this expression. We can also subtract par on both sides, giving us that 0 is equal to. Plugging the definition for delta in, we get par over 2 minus 2 times alpha. We know what beta is. Beta is the same as, this was here, par over 2 minus alpha. So if we have negative beta, we have negative par over 2 plus alpha, and then plus alpha prime. Woohoo! Oh, hell yeah, par over 2 is going to cancel out. We have negative 2 alpha plus alpha is equal to 0, being equal to negative alpha plus alpha prime. And now by adding alpha on both sides, we are going to get that the reflection law inside of the parabola, fuck off, holds if our rays of light go in parallel to the y-axis and pass right through the focus of a parabola. Et voila, I think this was one of my most favorite proofs here on this channel ever, and I hope you did enjoy what you have seen today. I had so much fun. There was such a cool derivation, and I'm 100% certain that there is a way easier way to do this trigonometric stuff right here, just using simple other things, elementary geometry things, but this was a lot of fun. And I found out a cool new addition formula, namely that 1/2 times the cotangent of alpha minus the tangent of alpha is the same as the tangent of par over 2 minus 2 alpha. You probably didn't know this before. I thank you guys for watching. And if you did enjoy what you have seen today, make sure to become a patron to support the channel even more. And until next video, you guys, a flammable day. See ya.